Hello and welcome to today's class. So it's the last class we are having on integration, and we are going to look at application of integration in kinematics, which you already know is a study of motion. So basically, we're dealing with displacement, velocity, and acceleration. And you may as well recall that when you were doing derivation, we said that when you derive displacement, okay, you get velocity function, and when you derive velocity function, you get acceleration function. And so the reverse of that is true. So if you have acceleration function and you integrate it, you will get a velocity function. And when you have velocity function, you integrate it, you will get a displacement function. So right here, we are having a particle that moves in a straight line, okay? Okay, basically we have a particle moving in a straight line through a fixed point O. And this particle is traveling with the velocity at a velocity of 4 minus t millimeters per second. So that is what the velocity is. The function actually describing the velocity of this particular particle. So we are supposed to find an expression for its displacement s from this point, given that s is 4 when t equals to 0. So basically, we've been given velocity. And remember what we said, that when we are looking at derivation, we said differentiation, that is, we said that when you're given displacement, okay, and you differentiate, okay, okay, when you differentiate with the respect ds with respect to t, all right, because displacement is always a variable of time, okay, then you will always get a velocity function. And then when you go ahead and you differentiate the v with respect, that's the function describing the velocity with respect to time, then you will get what we call an acceleration function. All right, so when you go the opposite of that, so when you integrate acceleration, okay, in effect you're going to get what? You're going to get the reverse of whatever you got before you went to acceleration. So remember, integration is just the opposite of derivation, okay? So when you integrate acceleration, you'll get velocity, and when you so we can actually have a back and forth there. So when you differentiate acceleration, you get velocity, and when you integrate, okay, velocity, you get differentiation. So you just have to know when you're doing what, to know what you're dealing with. So in this particular case, we have been told to find displacement, and we've been given this velocity. So basically that means that we're going to have to integrate velocity that we've been given, that is 4 minus t, to get displacement. So basically the integration of v with respect to t, dv dt, okay, in this particular case, we've not been given any limits, will be equal to the integration of 4 minus t, of course, with respect to t. And notice that this here will give us, when we integrate 4, we are going to get 4t, okay, because the value of the index value of t here is actually 0, and so when you add 1 to that, you get t raised to 1, and that is 4t minus 2 squared, okay? So of course, when you have t squared, you're going to divide it by 2 as well. And of course, given that this is an indefinite integral process, we're going to add our constant c to it, and we are saying that that's because we don't have any limits, okay? If you had limits, we would not have done that. So this here is our prearranged displacement function. This here, 40 minus t squared all over 2 plus c is what we expect to be the value of s. Is what we expect to be the value of s. However, when you read the statement further, we are being told that what should be the displacement s from this point if s is equal to 4 when t is equal to 0. So basically, what we're going to do, we're going to substitute s with the value 4 and t with the value 0 to solve for the unknown value of c. Then find the correct equation that is actually describing the displacement of this particular particle. So basically, we are going to have that s, which is equal to 4t minus t squared all over 2 plus c, okay, will be equal to, so wherever we have s, we're going to have 4, will be equal to 4 being equal to 4 into, and wherever we have t, we're going to have 0, minus 0 squared all over 2 plus c. So notice that our equation will then go down, will then be simplified to 4 being equal to 4 times 0, that is 0 minus 0, okay, plus c, which basically means that the value of c there is actually equal to 4. And so the correct function describing the displacement of this particular particle s will therefore be equal to 4t. Okay, so whatever we add now, in place of c, we're going to have 4. So that will be equal to 4t. Okay, let me have it as equation 1 here. 4t minus t squared all over 2 plus 4. So where we had c here, now we're going to have the value 4, as you can already see from that particular workout. So that's it for that particular problem. Let us handle the last example, then call it a day. Yep. For the second example, we having that a ball is thrown upwards with a velocity of 40 meters, and we are supposed to determine an expression for its velocity in terms of t. All right. So that is part A, Roman 1. Determine the expression in terms of t for its velocity. All right. So the ball has been thrown upward, okay, with a velocity of 40 meters per second. So that is what we know, and we're supposed to find its velocity. Then we also supposed to find the expression in terms of t for its height above the point of projection. So at that point, when it's just about to be released off to the space that it's being thrown into, what is the function or the expression describing that movement in terms of t. All right, that's the displacement. So we are supposed to solve for A, having taken into consideration the acceleration due to gravity to be equal to 10 meters per squared second. So not to worry. Remember, if you have acceleration, then you can always integrate and come back to velocity. All right, so from integration, you can always come back to velocity. Then from velocity, you can always come back to displacement. Awesome. Due to integration, of course. All right, so I want you to note that this ball is being thrown upward. Okay, so this ball is being thrown upward. It is not being thrown from a raised point now going down. All right, it is being thrown upward. So it's going against gravity. It's going what? Against gravity. It is not going due to gravity. It is going against gravity, not due to gravity. So basically that means because it's going against gravity, we will use the acceleration due to gravity not as a positive number but as a negative number. All right, so because the ball is being thrown upward, therefore, okay, due to the resistance due to gravity, the acceleration will be described as a negative number there. So basically, our acceleration when the ball is thrown upward will be, so A, when the ball is thrown upward, will be negative 10 meters per squared second. Okay, so that means that our velocity, that means that because we're supposed to determine the velocity, that means that our velocity, which is v, yes, that means that our velocity, which is v, is going to be, our velocity, which is v, is going to be equal, to the integration of acceleration, which in this particular case happens to be negative 10. All right, negative 10 with respect to t. All right, and therefore I want you to note that when you differentiate negative 10 with respect to t, you're going to get negative 10 t, negative 10t plus c. So we are adding c. Why? Because this is an indefinite integral problem. It's an indefinite integral. It does not have any limits. So it's going to be negative 10 t plus c. However, this is not where we leave our answer. So I'm going to call this equation 1, okay? That is not where we're going to leave our answer, though. We can go ahead and solve this particular problem easy. Why? Because we've been given the value for v, when t is 0, before the launch, when the ball is just about to be launched up, the value of t was 0, and the value of the acceleration of the ball, was actually 40. Right, so the force behind the ball was 40, and the time before it was released upward, it was actually what? It was actually 40. It was actually 0 minutes. So therefore, keeping in mind that t at the point of projection was 0 and v was 40, we will substitute these values for v and t to find for c. So basically, v is equal to negative 10t, plus c. All right, and we know that at the point of release, v was equal to 40, and t was equal to, so it will be negative 10. T was equal to 0 plus c. So at that point when the ball is just about to be released, I hope you're following that. T was 0, and the force behind the ball before the release was 40 meters per second. So it wasn't traveling yet. That was just the force behind the projection. So basically that means therefore that our value for c is going to be 40. This is going to be 0. Our value for c is actually going to be 40. Hence, the equation describing velocity of the ball being projected will be given by, so v will be equal to negative 10 t, negative 10 t plus 40, and that will be our answer for Roman 1. That'll be our answer for A Roman 1. Now, A Roman 2, we already have a velocity, so that's gone. I want us to think of A Roman 2. So A Roman 2, we are supposed to determine the displacement expression, or the equation that is actually showing the movement of the ball as it is being thrown, as it is being projected into space. What is actually the equation that describes the movement of that ball, the distance that it has covered upward, as it was being projected. So we have v, so we can therefore differentiate, integrate v to find s, to find displacement. So when we differentiate, so s basically will be given by the integration of v dt. The integration of a velocity will give us the value for s, which in this particular case will be the integration of negative 10. We can have it as will be the integration of negative 10 t, plus 40 with respect to t. And so notice that the value of s will be given by Okay, so when we integrate negative 10t, we are going to get negative 5t squared. I hope that by now this should come naturally to you, how the integration of negative 10t has actually been found. Okay, all right, so and plus 40t plus c. Why? Because it's an indefinite integration. We don't have limits. Plus c. So we are faced with a task to then go ahead and find the value of c, which in this particular case we can easily find. So I said that at that point when the ball is supposed to be, is just about to be released into the air, how much distance will it have covered? No distance. It is just about to be released. Okay, so it has s. The value of s there will be 0. Okay, the value of s there will be 0. And also note, at that point when the ball is just about to be projected up into the air, how much time has it covered has been counted already? 0. Basically, time hasn't moved yet, because time starts counting immediately the ball leaves and start traveling upward. All right, so at that time, time is also equal to 0. So s equals to 0 and time equals to 0, and therefore we use the value of s being equal to 0 and t being equal to 0 in this particular expression to find the value of c. So s will be, we'll have 0 equals to negative 5 into 0 squared plus 40 into 0 plus c. So basically, this means that the value of c, because this will be 0 equals to 0 plus c, the value of c will be equal to 0. Hence, the expression describing the expression describing the projection of the ball at the point of the expression describing the distance of the ball at the point of projection, or the height of the ball above the point of projection, will be given as s being equal to negative 5t squared plus 40t, since the value of c there is actually equal to 0. And so that will be it for that. All right, so we are going to use these values for v and s to solve other problems, all right, related to the same question, of course. So this was part A. We're going to part B of the problem. Yes, so we continue from where we left at B. So continuing the same question, we're supposed to find the velocity of the ball, and the height. Okay, so we're supposed to find its velocity and its height. Okay, that is at 2 seconds. All right, and at 5 seconds and at 8 seconds. All right, so we are having the velocity, a function here, and the height, the height expression. Okay, as our equation 2 right there. And I also hope that you have your calculator. All right, because this is going to be, all issues of, substitution, direct substitution into the equation. All right, so for velocity at Roman 1 at 2 seconds, okay? So for velocity at 2 seconds, we are having that v will be equal to negative 10, okay? So wherever we have t, as t was describing time, all right? So wherever we have t, we're going to have 2. So it will be negative 10 into 2 plus 40, all right? And so v at 2 seconds will be negative 10 into 2 plus 40. And that will be 20 meters per second. So that will be the velocity at that particular second, okay? The velocity being traveled by the ball at that particular second will be 20 meters per second. And the displacement at that particular time will be given by negative 5. So it's negative 5 into 2 squared. Our t value is 2, t squared, so that's 2 squared, all right? Plus 40 into 2. So our s, our height at 2 seconds will be, of course, that's negative 5 into 2 squared plus 40 into 2. Of course, this will be 60 meters. Okay, so the height that the ball will have covered at the second at the second second at the second, right? After 2 seconds, or that is after 2 seconds, will be 60 meters. So that height after 2 seconds of being projected upwards will be 60 meters, and it will have covered that at the velocity of 20 meters per second. Interesting. So why don't we go ahead and solve for Roman 2? So at the fifth second, our v will be equal to, okay, velocity will be equal to -10. Okay, we are substituting into equation 1, and now in place of t we are putting 5. So it will be -10 into 5 plus 40. All right, very, very easy, nothing complicated there. So that's going to give us -10 into 5 plus 40. Yes, that's going to give us -10 meters per second. Yes, it will give us -10 meters per second. So what that means basically is at the fifth second, speed will have reduced. Okay, so it started with 40, then at the second it was at 20, and now we're expecting that we're seeing that at what? At the fifth second, it is -10. That is to mean that probably the ball is going down. It has already reached the maximum height, and now it's coming down. It's coming down. Sorry, it's coming down. All right. So basically, that's why we are having -10 as the velocity there, and of course, our displacement will be directly into equation 2, where we have t, we put 5, so it will be -5 into 5 squared, okay, plus 40 into 5, plus 40 into 5. That's the fifth second. All right, so what do we get there? We're getting -5 into 5 squared plus 40 into 5. So at this particular time, that's the fifth second, the height that the ball will have covered will be actually 75. So this means that the ball isn't really going down. Okay, this means that the ball has just slowed down. Okay, the velocity has just kind of slowed down to yes, -10 there, to 10 probably. All right, so yes, just a minute. Yes, why don't we look at the velocity, or the velocity and the height of the ball at the 8th minute. By this time, I expect that it should be easy for you, and maybe I can let you go ahead and do it yourself. So you can pause the video and see what you get. All right, so if you're getting these answers for Roman 3, then it means that you have understood what's being done. So at Roman 3, your velocity should be equal to -40 meters per second, and yes, probably at that time it was just coming down. Yes, and the height of the ball should be equal to 0 meters. So at that point, the ball has landed. It has fully landed on the ground. Okay, the ball has landed. All right, so it doesn't have any velocity, it doesn't have any movement. Okay, it doesn't have any movement. It's landed already. It's landed. All right. So at the fifth second as well, when the velocity was -10, we assume that the ball was now on a downward projection. So remember, you throw it, then it reaches at some point, then it starts coming down. So when it's coming down, you measure the velocity in terms of a negative number. So that is why we see that the velocity here is -10, right? Okay. So I'm probably wondering what the highest maximum distance was after the projection. Okay, and so let's see, maybe the third question asks that, and maybe the third question wants us to answer that. So why don't we do the last bit of this particular chain of questions, that is part C of this question, and then see where it leads us. Yes, surprise. So the third question actually wants to know the maximum height that the ball attained after the projection. So find the maximum height attained by the ball. Find the maximum height attained by the ball. All right, so I want to submit it to you. I want you to understand this, that when you throw this pen or this ball on an upward projection, then it reaches its maximum height. What will happen? It will drop. All right. That means that at that point, when it has reached its maximum height, the velocity or the speed with which it was traveling actually was 0. That is why we are moving from 40 going to 0, and now we start counting with negative, -1, -2, -3, -40. It's down, right? So the point when the ball reached the maximum height, the velocity was actually what? 0. And so we want to keep that in mind as we try to find the maximum height attained by the ball. So basically that means that we are going to have V being equal to what? Being equal to 0 here. So the point when the ball achieved the maximum height, we expect that V is supposed to be 0 meters per second. That is the speed of, or the velocity of the ball. All right. So basically we're going to have, we're supposed to find the maximum height. Yeah. So that is, so we have that V is equal to that. And what else do we know? Yes. All right. So basically we are going to use this concept to find also the time at which the ball reached the maximum height. All right. So we are going to come to our expression that is actually describing the velocity of the ball, and equate V to 0. So basically we're going to have that 0, where in place of V is equal to -10t, right, plus 40. All right, so for us to find the value of t, let's have 40 on the left hand side, so that's going to be -40 equals to -10 t. That means that our value for t, when you divide both sides by -10, will be 4. So it is at the 4th second, that the ball actually reached the maximum height. And that is why you notice that when you are doing the previous question at second 5, at the 5th second, it started dropping, and now the velocity was from 0 to a negative number, right? -10. So a positive to 0, then 0 to negative. So the point when the ball reached the maximum height is actually the 4th second. I hope we are in agreement there. So if we know the time when the ball reached the maximum height, then it becomes easy for us to find the maximum height. If we know the time, we just substitute 4 into the expression describing the height of the ball after projection. So wherever we have t, we are going to use 4 in question 2. All right. So for us to find the maximum height, we will then have s being equal to -5. In place of t, we put 4. 4 squared plus 40. Okay, -5, 4 squared plus, was it 40 or 40t? Let me find out. Yes, it was 40t. Yeah, I forgot a t here. Yes, plus 40t. So it's going to be plus 40 into 4. Yes, plus 40 into 4. All right, so that's going to be -5 into your calculator, times 4 into 4 squared plus 4t, 4e, times 4. Yep. And so you are expected to find 80 meters. So the highest height that this ball actually covered after being projected was 80. So it moved from 0 meters per second up to 80, and then from 80 it went back to 0. And that is a story of motion told using integration. All right? Just by knowing acceleration and the velocity of the ball before the projection, and the acceleration due to gravity. All right. So that's it for this particular class. I would have loved to have given a bonus example, but that will prove to be lengthy. All right. So maybe I may drop in a bonus example later on, or even never. But I'll see you and in the next video, and have a beautiful and lovely day.